And we have a range of these glass ceramics. In the past, we had these mica-based systems, the Dicor, which are no longer popular, but again, these were classic fluoride or mica-based systems. We had the lucite-based systems. We had the recent systems where people such as IPS Design with Everclar are putting both a calcium and a fluoride system, so we're getting a fluoroapatite structure in those systems. We can get these systems such as the Zerg press, which has again got a phosphofluoride-based system, and then we've got things such as the lithium disilicate materials. Now, what you notice with this is, particularly with the lithium disilicate, there's a very, very, very high concentration of crystals in it, typically up to 70%. With most of the others, we're talking about 10 to 20% of crystalline phase. And again, I think you have one of these machines in your department, so you're very familiar with this approach. Now let's move on to the non-ceramic systems, the non-silicate material systems, where we have, for instance, the alumina, such this may be the in-ceram material, where we have this matrix phase of a crystalline alumina, which is then infiltrated with the lithium silicate glass, or lanthanum silicate glass. We can have the Procera alumina, such as here, which is just completely polycrystalline grains of alumina or alpha alumina, and then we have the zirconia that is on this side here. And the big feature you notice between these two systems is that the grain size in the alumina is typically 2 to 3, 4 microns, whereas in the case of the zirconia, it is submicron. And it has to be submicron because if it gets bigger than micron size, then it's too metastable. It will transform on cooling from the tetragonal structure to the monoclinic structure, and the strength will be greatly reduced. Now, this is the big aspect that has made zirconia so attractive. This ability to do this, what we call soft milling, where we can press these powders, and they typically come with these little spray-dried powders that are made up of very, very fine nuclei of zirconia. These are pressed together in a uniaxial conditions. They've then got a relatively low density. The density may be only something like 50%, and the strength is relatively low. They're relatively soft, so it's easy to machine these materials. And the way we do that is pre-sinter these at 1100 degrees centigrade. Very simple and straightforward. After it's sintered, it can be read with this pre-sintered conditions. It can be shaped and cut very easily, and then we have to go to the final stage of sintering this, typically between 14 and 1500 centigrade. And the consequence of that is that we get this reduction. So initially the green material is machined in this dimension, and so it's oversized, and then after sintering it is sintered and shrinks 25%, and we get this as the final stage. So the CAD-CAM is important because it can expand the size of the system to mill, and then hopefully if we've got the shrinkage parameter correct, it will be fit precisely outwards. We're doing some work in Dunedin suggests that the fit is not quite as good as we'd like. And then we can often hear people talk about hipping. Hipping is what we call hot isostatic pressing, because when we sinter the material, there may still be small defects present, small porosity. But hipping by hot isostatic pressing with high pressure and gas, we densify this so that the strength is much greater. And so we can do this systems, and this is very common now, where different companies have got these devices. There is now availability of colouring liquids, such as these are usually iron-based colouring liquids, iron chloride, iron nitrate, and dipped in these systems, and depending on how many dipping processes, you can change the value of that material to match more closely the type of features that you want. And you see here this dramatic change in the colour of these, from these very tombstone white colours to much more realistic mouth colours. Now I want to also talk about strength and toughness of these different materials. Many people I found in dentistry confuse strength and toughness. They think they are the same, but really strength is a measure of the strength of the material if we put it usually in bending. So here we have a situation where we have a 3-point bending, and the strength is related to the dimensions of the beam and the load. But the strength of the material is really dependent upon the fracture toughness of the material and the defect size. So the way we measure fracture toughness is typically, as in here, where we put a small notch in the material, we load that material up, and we cause it to crack. So this fracture toughness, or K1C, is a much more fundamental basis, and this is why the strength of the material changes. The toughness stays constant, but because the defect size, or the crack size, this value of A in that top equation, is different, because of the different treatments, different porosities, etc., then this will influence the strength of the material. This does not happen with metals, because metals usually have plastic deformation before fracture, and so we don't have to worry so much about this, we worry about yield. But brittle materials, it is the defect size that is important. And this is where you guys have a role. Your adjustments of your materials introduce defects. So what are the microstructures of these materials, and what are the mechanical properties? So here are the different microstructures we've been talking about. And what are the mechanical properties of these systems? So here we have this Zerpress. These are the different materials, and so this is a feldspathic porcelain which has got lucite in it, the Empress 1, Empress 2, the Insuran, etc. So what are their mechanical properties? And here is the crystalline phase typically of these materials, and we can see that in these materials that there's a crystalline phases, and the nanofluoroapatite is very small at 10 or 15%. The lucite, the Empress 1 were about 20%, or even higher, up to 30%. The lithium disilicate were up to 70%. And then in the Insuran material, we've got about 20% or 25% lanthanum silicate glass, and then the Insuran zirconia. And then in the Procera alumina and the zirconia, there's virtually no glass. These are complete non-silicate ceramic materials. And what are the mechanical properties of this? Well, they start this value of about 90 megapascals. They go up to the lucite materials with increasing amount of lucite. We're going up higher and higher. But notice that with the lithium disilicate, we get a dramatic increase in toughness and strength. Why? Because of all those little needle crystallite structures that are present. Then if we go up into the other materials, we're going up now strength up to 600 megapascals, and even a little bit higher with the case of zirconia in that system. And then we move to the two crystalline materials. And it is this issue that is making zirconia so attractive. This strength is very high, up to 900 to 1000 megapascals, and also that there is this very, very high fracture toughness. When you compare that with some of the alpha materials, you see there's almost a factor of 10 between these processes.